Howdy. Today I'll be solving the 2017 final exam, Physics 207, to hopefully help you prepare for the final. So let's get started. So problem 1, we want to write Maxwell's equations in integral form. Remember that there's 4 of them. The first one being Gauss's law, which is a closed surface, which is E dot ds equals Q enclosed over epsilon naught. And then we have Gauss's law for magnetic fields, so that'd be a closed surface or the flux as well of B dot ds. This one's equal to 0. The third one is Faraday's law, which is now a closed loop of E dot dr. It's equal to the negative partial respect to time of the magnetic flux, just B dot ds. And then Ampere's law with Maxwell's modification. It's a closed loop, B dot dr is equal to mu naught I plus the displacement current, which is epsilon naught partial derivative with respect to time of the electric flux, which is E dot ds. And the main thing here is you put the loops where they're supposed to be and the arrows, the vector notation on top of what needs it. Otherwise, you may not get the credit for the equation. So for number 2, we have a Coulomb's law problem. So we have 3 charges that are placed as shown. Their distances A and B are labeled. The charges Q1 on the x-axis are known and positive. And the charge Q2 at the bottom is unknown. And it's asking, what must be the unknown charge if the electric field is to be 0 at x equals 0, y equals h, where here h is unknown. So remember that to find the electric field, we have force is QE, right? So then the electric field would be the force divided by Q. Or in the book, it has it as Q naught because we're using a test charge, and we're basically going to divide by that. Where in this case, it didn't label the charge at y equals h, so that's what we're going to end up calling the test charge. So this will be Q naught. So, and then the force formula as well, for Coulomb's law, it's Q1, Q2 over 4 pi r squared epsilon naught. So now let's start labeling a free bar diagram where the point of interest is at x equals 0, y equals h. So my Q1 charges are positive, right? And then I'm just going to make my test charge Q naught positive as well. Therefore, these will repel each other. So this will have a force, call it F1 or something, going this way, which will have some sort of components. And then I would have this other Q1 going this way as well. And the reason I did it in the same color is because these are the same charge and they're the same distance away. So therefore, the force on the left is also going to be F01. So with that, with that, I can say that if I just look at the triangles I drew, I see that I'm going to have my x components cancel, right? Because I have one x component going to the left and another one going to the right. So then here I can say from symmetry, the sum of the forces in the x direction are equal to 0 because they're going to cancel out. And then to find a theta, well, I can just say that I put a theta here, therefore my theta will be up here as well. And that will apply for both of these, but we just need to use one of them and then multiply it by 2 essentially, so it's fine. And then for the unknown charge, because it's unknown, typically you just choose for it to be positive or negative and then just go with that. In this case, I'm going to assume that it's positive. So then this is going to end up repelling and creating a force up here. So I'll call this one F of 2. But we're only dealing with y components, so I can just write the force in the y direction. Now I'm going to pull out the constants, which is 1 over 4 pi epsilon naught. And then if I look at my force 1, I'm going to have 2 of those, right? I could just add them up twice, but it's easier to just multiply one of them by 2. And that force created by the blue vectors would be Q1, Q0, divided by the radius. Well, the radius would be this r right here. And the radius would be, from Pythagorean theorem, we have r squared is equal to the base squared, which is a squared plus the height, so plus h squared. So this is a squared plus h squared. But we want the y component. And with the theta that I chose, the y component, the trig function that would give me the y component would be sine theta. And then I want to add the other force, the F2 force, which is going to be Q2, Q0 divided by the radius. Well, this distance here is B, and this distance here is H. So my total distance is going to be B plus H. So my radius squared will be B plus H squared. And we want the inside equal to 0 because we want the electric field to be equal to 0. But before we can do that, we need to find what sine of theta is. So sine of theta is opposite, which is going to be H, over hypotenuse, which is just the radius. So I can just take the square root here of both sides. So radius is square root of a squared plus h squared. So that's what's going to go down here. So now I can bring this back into here. So I have 1 over 4 pi epsilon naught 2 q1 q0 over times sine theta. So I would have the a squared plus h squared with the first power plus to the a squared plus h squared to the 1/2 power. So then I'll be left with a squared plus h squared to the 3/2 power, and then the h on the top from right here, from the sine. And then I would just add the other one, so q2 q0 over b plus h squared. But this is the force, and the question was asking me for the electric field. So remember, the electric field is just the force divided by the test charge. So this would be 1 over 4 pi epsilon naught 2 q1, and then the q0 goes away, so h divided by a squared plus h squared to the 3/2 plus q2 divided by b plus h squared. And we want this equal to 0, so the constant can obviously never equal to 0. So what we want is we want this inside piece to equal to 0. So we're going to have 2q1h over a squared plus h squared to the 3/2 plus q2 over b plus h squared is equal to 0. And the unknown charge in this case is q2. So we want to solve what q2 needs to be. So I'm just going to move this to the right. And then I'm going to multiply by b plus h squared. So I'll get q2 is equal to negative 2 q1h b plus h squared divided by a squared plus h squared to the 3/2. And that would be the answer. So the main thing on this one was just remembering that the electric field is the force divided by the test charge. In this case, I called it Q0. Doesn't really matter what you're going to call it because you're going to divide by it either way. But typically we use Q0 to refer to. For problem number 3, we have a rod with resistance R. So it's important to check if it has or it doesn't have resistance. In this case, it does. Slides without friction on the tracks, yeah. Go to capacitor C. A wire carrying a constant current I0 is parallel to the tracks as shown, and it wants us to find the direction of the current in the loop. So, and it wants us to explain like a reasoning for that. So the way we're going to do this with Lenz's law. But before we can do that, we need to determine what direction the magnetic field is. So the way I do that is I find the magnetic field and then I figure it out by using my right hand. So remember, for an infinitely long wire, the magnetic field, it's a closed loop, of B dot dr is equal to mu naught. In this case, it's just I. We don't have to worry about displacement current here. So if I draw my loop like this, I would have B 2 pi r is equal to mu naught, and the current enclosed by that loop is going to be I naught. So I get B is mu naught I naught over 2 pi r. And in terms of the direction, well, you point your thumb in the direction of the current, right? So it's like pointing to the left, and then you curl your fingers. So in the bottom part where your fingers are, initially, they're pointing out. So this is going to be out. And then when you curl them back around the wire, you get that they go in. So on this side, it goes in. But we only care about where the circuit is. So the magnetic field is going to be pointing out. So I will put something like B is out or something for reference. And then now we can apply Lenz's law now that we know the direction of the magnetic field. So in this case, we're pulling the rod to the right, right? So as we pull this more, so let's say like the rod is now here, for example. The area here of this circuit is greater than the area when it was just at this point. So that means that as we pull it further to the right, the area is increasing. And because the area increases, that means the flux also increases. And when this happens, B self is going to oppose. So B self is opposite of B. So B self is, if it's opposite, well, B we determine is out of the page. So that means B self is going to be into the page. So current will be, well, point your thumb into the page. The ways your fingers curl, it tells you the direction of current. So current is going to be clockwise. You can put like by Lenz's law or something. But that's why. So then current's going to be clockwise. So it's going to be like this. And because current's going this way, I typically like to put plus Q where the current is going, just so I can always say that current is positive dq dt. I don't have to worry about if it's negative or not. I find that easier just to make it positive, this where the current's going. So, and then by convention, I'll go around the loop this way with ds pointing out of the page. If you were to do it the other way, then ds would go into the page. But the way the book does it is like this, so I'll do it like this as well. So now part B is saying, ignoring self-inductance, find the charge on the capacitor. The capacitor is a function of time when the capacitor was uncharged. So that'll be our initial condition, that it's uncharged. So this is saying that at Q at T equal to 0, it's equal to 0. And for this one, we're going to use Faraday's law. So the closed loop, V dot dr, is equal to the negative partial with respect to time of the magnetic flux, B dot ds. So let's start by finding the flux. So we have the integral, B dot ds. Now it's important to check if the magnetic field is constant. If the magnetic field depended on time or just had random constants, then we could pull it out. But if it depends on distance, like x or y or r in this case, it has to stay in the integral. So inside it's going to be mu naught I naught over 2 pi r. And then we need to determine the area. Well, as we pull the rod to the right, this distance right here will change, right? So we'll call this x, right? So like over here will be a different x and so on. So this part will be x. And then the height of the rod, well, if I keep creating more loops, right? More magnetic loops. This height here, or I should do it in different colors, easier to see. This height here is not going to be the same as if I had a loop and had this height here. So what we're going to need is let me just keep one for reference, I guess. We're going to need a slice of this height essentially, and we'll call this dr because from here to here, I'm saying this is r, so then this whole distance will be r as well. So then my area is going to be x, which is changing, and then dr, which is also changing. And one way to check if you're correct as well, you're going to be integrating over r. So you're going to need to have dr or dx or dy, whatever, one way or another. So, yep. And then our bounds of integration is going to be where the circuit's at. So it starts at A, and then it goes up to B. So from A to B. If B started here, then it would be A plus B, but because B covers the whole distance, it's just B. And now I need to check if it's going to be positive or negative by the dot product. So I said ds was coming out of the page, and my magnetic field down below the infinite water is also out of the page. So then my integral is going to be positive. So this is fine. So now I just need to evaluate it. So this is going to give me mu naught I naught x over 2 pi 1 over r. The integral 1 over r is ln of r. If I plug in my bounds, it will be ln of b minus ln of a, or combine it into one log, so you get ln b over a. Now I want to find the time derivative of this flux. So I will get mu naught I naught over 2 pi ln of b over a, and the only thing I can differentiate is the x, so this will give me dx dt. And, well, is it positive or negative? Well, I'm pulling the rod to the right, so dx dt is getting greater, the area is getting bigger, so this is going to be positive. So positive v. If it was the velocity was going to the left, then you would say it would be negative because it's getting smaller. So just rewrite it. Mu naught I naught over 2 pi v ln of b over a. And the last thing we need to do is we need to go around the loop and then set it equal to this. So if I go around my loop, I touch, like if I go the way I put ds, I'm coming down the loop. I touch the negative plate of the capacitor. So this will be negative q over c. And then I keep going down and I climb up the wire, but my current's going the other way, so I'm opposing it. So it's going to be negative I R, because the wire has a resistance R. And then this is equal to negative from the law. Don't forget that negative. And then the answer we found. So mu naught I naught v over 2 pi ln of b over a. And I can divide by negatives on both sides. So I will get q over c. And then I want to find the charge as a function of time. So I'm going to convert current, I, into charge, which the relationship with that is current is dq dt. So I would have dq dt r is equal to mu naught I naught v over 2 pi ln of b over a. And now we want to solve for it, so we need to recognize that this is a non-homogeneous first order diffie q. It's non-homogeneous because the right side does not equal to 0. So when we are in this case, q of t is going to be q particular plus q homogeneous. If the right side was equal to 0, we would only have q homogeneous. So let's begin solving. So qp is in steady state. So all derivatives with respect to time equal to 0. So if I reference this equation, I will have 0 plus qp over c is equal to mu naught I naught v over 2 pi ln of b over a. Multiply by c on both sides, I get qp is equal to mu naught I naught cv over 2 pi ln of b over a. okay? And then Q homogeneous, remember Q homogeneous for first orders, because it's different for second orders. For first order, which means the first derivative is going to be alpha e to the negative beta t. And then I just plug that in wherever I see it. So for the derivative, it's going to be itself alpha e to the negative beta t. And the chain rule, so negative beta, times the resistance R, plus Q, where Q is alpha e to the negative beta t, over C. And this is the homogeneous solution, so we set this equal to 0. And in this step, you always solve for beta. So divide by alpha e to the negative beta t. You get negative beta R. I move this to the right. It's equal to negative 1 over C. Or that beta is 1 over R. The last thing you gotta do is just plug everything together and then use your initial condition to find alpha. So we said Q at T was Q particular, which is mu naught I naught CV over 2 pi ln of B over A, plus Q homogeneous, which is alpha E to the negative beta T, which is negative T over RC. And now we use our initial condition to find alpha. So at QT equal to 0, we were told that the capacitor was uncharged. So we're gonna plug in 0 for everywhere we see T, and then set that equal to 0. So we will get mu naught I naught CV over 2 pi ln of B over A, plus alpha e to the 0, which is 1, so I can just ignore that. This is equal to 0, meaning that alpha would be kind of out of space. So I'll put alpha is equal to negative Q particular, right? So then Q at T would be, if I factor everything out, I would get mu naught I naught CV over 2 pi ln of B over A. And then I would have 1 minus E to negative T over RC. And that's the answer for this part. So the main thing is just remember that you need what's it called? Remember that Q homogeneous for first orders is alpha e to negative beta t, and Q particular means at steady state you set all the time derivatives equal to 0. That's pretty much it. Oh, and then part C, you want to plot it schematically. So if we look at the answer we got, what I recommend is this, like the 2 points to pick to plot it is to pick time equal to 0 and pick time equal to infinity. So if I were to say t equal to 0, the only thing that depends on t is the exponent, right? So I would have 1 minus e to the 0, right? E to the 0 is 1, so I would have 1 minus 1. So this equals a 0. So then when I multiply anything by 0, it's 0. So at time equal to 0, I'm starting down here. Now let me do the same thing, but as time goes to infinity, I would have 1 minus, and then I can rewrite the exponent. The exponential is 1 over e to the t over rc, right? If I plug in infinity, I will get 1 minus 1 over e to the infinity. This will go to 0, so then I'll have 1 minus 0, so this is equal to 1. So as time goes to infinity, it's eventually going to equal to 1, meaning it's going to equal to all the constants in front, so all of this. And all of this is QP. So at some point, it's going to get to QP. I just write QP. It looks something like this. That's it. So for problem number 4, we have a loop with currents I1 and radius R. So this is a radius of R. Find the magnetic field created by this current at x equals d. So for this one, if we find magnetic field, this isn't an infinitely long wire, so we're gonna need to use Biot-Savart's law, which is dB is equal to mu naught I over 4 pi ds cross r over r cubed. And I believe these are given in the back. Yes, it's right here. So to find the magnetic field, we essentially consider the two endpoints of the circle as if we went around the entire thing. So if I start at the top, and then I go to my point of interest, this will be in radius of r. And then to find the magnetic field here, if I put my palm on top of the circle, so my fingers are pointing towards me, and then I curl it in the direction of r, it's not like straight, it's like at an angle. My thumb is a little bit at an angle. So you should get that your thumb points somewhat in this direction. And this would be dB. Then if I repeat the same thing for the wire down here, but now my fingers are going in, and then I need to kind of curl it. It's kind of hard, but if you curl it, you would get that for the bottom part, your thumb points to the bottom right, so you would get a dB down here. So we can see here that from symmetry, the sum of the magnetic fields in the y direction this time are equal to 0. So we only need to worry about the magnetic field in the x direction. So I can just write that dB of x is equal to mu naught, the current I1 over 4 pi ds, right? And then cross r, but in this case we just determine it's in the x direction, so we can just have ds times r. So, because it's a right angle here as well. So ds cross r, I'll just leave it as little r for now, and divide it by little r cubed. So I would just have mu naught I1 ds over 4 pi r squared. But what is r? Well, this is r, right? The bottom distance is a distance x, and the y distance is r, the radius, right? So then r squared is going to equal to big R squared plus d squared. So this would be r squared plus d squared. But now the thing is, we want the x component because we know the y component is going to cancel. So if I were to introduce a theta here, I want to find where that equivalent theta will be another triangle. So the way I do that is, if I look at where the theta is, right, the two lines in between them, I have this line in green, right? And basically, I want to see what line that I made on my triangle is perpendicular to this green line. So if I stretch this out, this vertical line, this is perpendicular to it, right? And then if I do the same thing for the other segment, let me do this in red. I want to see which segment is perpendicular to this. Well, I already drew the 90 degree there, so it's going to be this one. So what this tells me is that the theta here between this red and green is going to be the same theta as the red and green in the top part. So then theta is going to be here as well. So that's how we can figure out theta goes there. So then, now that I know my theta is up there, that means to get the x component, I'm going to need sine of theta. So let's quickly find that. So sine of theta is going to be opposite with respect to the triangle on the left, because that's where I have my notes. The opposite is r divided by the hypotenuse, which is just a square root of the radius. So r squared plus d squared. So this is going to be mu naught I1 r divided by 4 pi r squared plus d squared to the 3/2. And the last thing I need to do is integrate, because I don't want dB, I want b of x, the actual magnetic field there. So b of x will equal to the integral of mu naught I1 r divided by 4 pi r squared plus d squared to the 3/2. Oh, I forgot the ds as well. ds should be here. ds. In this case, the only thing we're integrating is ds. So be mu naught I1 r over 4 pi r squared plus d squared to the 3/2. In this case, ds is just the length we go around. So this will be the circumference of the circle. So it would be 2 pi r. And if we simplify this, we would get mu naught I1, it's I1. Mu naught I1 r squared divided by 2 r squared plus d squared to 3/2. Right, because the pi's cancel out and the 2 over 4 can be simplified to 1/2. So yeah, that's how we do this first part. Now the second part, we have an infinitely long wire, radius a, and current I2 out of the page. And we want to find the magnetic field everywhere. So we'll use Ampere's law again. So if I create a loop in here at r less than a, I will get b 2 pi r is equal to mu naught, the current, which is I2, but then I'm going to divide it by the actual area enclosed, the total area of the surface, which is pi a squared, times the area of where my loop is, which is going to be pi r squared. So here I can see that the pi's cancel, one of the r's cancel. So I get b is mu naught I2 r over 2 pi a squared. And to determine the direction, well, it told me that current's pointing out of the page. So point your thumb out. The way your fingers curl is the direction of the magnetic field. So it's counterclockwise. And then for r greater than a, we would have b 2 pi r. It's equal to mu naught I2. And if I'm out here now, I'm going to have the same area, the actual area, pi a squared, times the area where my loop is, which is enclosing the entire surface. So it's also going to be pi a squared. So this will cancel. So then I will get the magnetic field is mu naught I2 over 2 pi r. And then counterclockwise as well. Now for part C, we have a negatively charged particle, negative q naught, and it's at the point x equals d. So we have the charge right here, negative charge again, with a velocity in the z direction, and it wants us to find the force acting on the particle. So remember, the formula for a force of a particle is force equals q v cross b. But the thing is here, it's negative, so remember that we're going to have to flip the direction that we find, essentially. So we need to know what directions the magnetic fields are going. So in the beginning, we already found the magnetic field in the x direction, right? So this is going to be b of x, where b of x is the magnetic field we found in the beginning. And now, to find the magnetic field created by the what is this, a wire? Yeah, the wire on the right, we would have to create a loop, like a Amperean loop that encloses this. And the thing with this one is you need to know that the magnetic field is tangent to this loop that we create. So when it hits this point D, it's going to be tangent to the circle I drew. So it's going to be going straight down like this. So this would be B of Y. So now let me find the forces. So the force is going to be Q, which is negative Q, V, which is V naught, cross B. So in this case, let's start with B of X. So then B of X is mu naught I1 R squared over 2 r squared plus d squared to 3/2. I believe that's right. Yep. And to determine the direction, well, velocity is coming out, right? Because the z is defined positive out. So it's coming out. And I chose to start with bx right now. So if I curl my fingers in the direction of bx, I get that my thumb points up. So this will go up. And this will be the F of y force. But because there's a negative, we have to invert this. So negative up is the same thing as positive down. So in reality, my force is going down. And because this is f of y, that means the next force will most likely be f of x. So if I repeat the process, I'll get negative q v naught. And then now I'm going to do it times by, where by, there's two by's, right? But the one on the left is when we're inside of the wire. The one on the right is when we're outside. And currently we're outside, so we're going to use the one on the right. So it's going to be mu naught. All right, 2 over 2 pi r. But in this case, we know what r is. We're a specific distance d, because we have 2d, and then minus d. So this distance here is d. So we have 2 pi d. And then if I do the cross product, well, velocity is pointing out towards me, right? And if I curl my fingers downwards towards by, I get that it goes to the right. But remember, this is a negative charged particle. So to the right is the same thing as, negative to the right is the same thing as positive to the left. And then you can just write that the total force would be f of x, ix, plus f of y, iy. That's how the answer key had it, so you don't have to rewrite all of that again. The main thing here is remember that you needed to flip your direction of the forces, because it's a negative charge particle. For number 5, we have a spherical conducting shell of inner radius A and outer radius B, and the inner shell has a charge of negative q naught. It is surrounded by another conducting shell of inner radius C, outer radius D, which has a charge of plus 2 q naught. So there's a plus 2 q naught out here. And part A is asking us to find the charge per unit area on all 4 surfaces. So remember that Q is equal to sigma ds. And it wants us to find charge per unit area, which is sigma. So sigma is charge, well, per unit area. So divided by A, the area. So the way we do this is we set the radius equal to the specific point. So r equals A. So I'm right here right now. Here, there is no charge on that. So sigma is equal to 0. And then r equal to B. I'm right here now. And here I do have a charge. I have a negative q naught. So I would have sigma negative q naught over the area at that point, which is 4 pi, and the radius is b here, so 4 pi b squared. Now for r equals c, here's where we need to be a bit careful, because we have a conductor in here, right? Which means we need that negative q naught to somehow get canceled. Otherwise, if we were to create a loop here, a Gaussian surface, we would get that there is charge, negative q naught. And that can't happen. So the only way we can have this equal to 0 is if we have a positive q naught charge lingering here. But then to basically undo what we did here, we're going to have the negative q naught lingering around out there. So at r equals c, we will get positive q naught divided by 4 pi. The radius here is c, so c squared. And then at r equals d, we have 2 q naught minus q naught, so that's just positive q naught again, over 4 pi c, no, not c, it's d this time. 4 pi d squared. So now for the second part, So that's going to find the electric field at basically every point. So if I create a Gaussian surface now, R less than A, there's nothing in there, so E is equal to 0, because charging close to 0. We're using Gauss's law, by the way, so E dot ds, it's Q enclosed over epsilon naught. Part 2, between A and B, I'm in here now, but I'm inside a conductor, so electric field is 0, remember, inside a conductor it's 0. Now I'm between B and C, so I'm out here. This time I am enclosing the charge now, so I have E 4 pi r squared is equal to charge enclosed, which is negative Q naught, over epsilon naught. So this will give me E is negative Q naught over 4 pi r squared epsilon naught, and then radially out. Now between C and D, again, I'm inside another conductor. So electric field is 0, because it's a conductor. Now for R greater than D, I'm out here, and my charges enclosed is going to be the 2Q and the negative Q. So I would have E 4 pi r squared is equal to 2Q naught minus Q naught over epsilon naught. This would give me that the electric field is equal to Q naught over 4 pi r squared epsilon naught radially out. Now part C is asking me to sketch the electric field lines. So if I start with the outside one, it's positive and radially out. So then my electric field lines are going to look like this. They should be perpendicular, nice and straight. Draw a good amount as well, just to be safe. And then for the other region, I have radially out, but it's negative radially out. So that flips the direction. So negative radially out is going to be the same as positive radially in. So then my electric field lines will look like this. Then part D, it's saying to find the difference in the electric potential between R equals 0 and R equal infinity. So and it tells us what to do on the very end. So V of infinity minus V of 0. Remember, this is equal to the negative integral of R1 R2. R1 is 0, R2 is infinity. The electric field dot dr. So what we have to do, we have to break this up into several integrals. So I'm starting at 0, and then I go up to A, but this is 0 dr, so that goes away. Then I have another integral starting at A, and I go to B, but that's also 0, so this is 0 dr, so this also goes away. So now my next integral will be from B to C. Here it's not 0, I have negative Q naught over 4 pi r squared epsilon naught dr. And then my next integral will be from C to D, but here it's 0, so this goes away too. And plus the last integral from D to infinity, here it's not 0, here it's Q naught over 4 pi r squared epsilon naught dr. So now I just evaluate. I have the negative from the formula, and then 1 over r squared, the integral of that, is negative 1 over r. So the negative in this integral is going to go away. So I'm going to get Q naught over 4 pi epsilon naught. I plug in my bounds. I will get 1 over C minus 1 over D. And then here, again, the integral of r squared is negative 1 over r. So I will have a negative here. So I'll have negative Q naught over 4 pi epsilon naught. You would have 1 over infinity, which is 0, minus 1 over D. And you could do it like this, and that'd be correct. So that's the answer to this part. Now part D, we have a non-conducting spherical shell, non-conducting now, so it's important. Inner radius A, outer radius B, has a non-uniform volume with charge density, rho equals CR. So whenever we're given something like this, where rho is equal to something, that's a clear indication that you're going to need to integrate over it. So here it's asking us to find the electric field at R less than A. Well, in this case, at R less than A, the electric field is still equal to 0 because it's empty, there's nothing in there. But now for the second region, when we're between A and B, that's where things change. So we have E 4 pi R squared is equal to 1 over epsilon naught, because in this case, charge is going to be equal to the integral of rho dV. So I'm going to have an integral of rho, which is CR, and dV. Well, if you don't know what dV is, we can kind of like quote unquote derive it, you could say. So the volume of a sphere is 4 over 3 pi r cubed, right? If we take the derivative with respect to r, we would get 4 pi r squared from the power rule, right? And then just multiply by dr on both sides, so you get dv is 4 pi r squared dr. And that's what we're going to plug in here. So 4 pi r squared dr. I'm going to pull out my bounds. Let's do my bounds first. So my bounds, I'm starting at A. And then I'm not going over the entire surface. I'm only going up to an arbitrary radius r. So I'm going from A to R. So I can pull out some of the constants. I can pull out the C4 pi over epsilon naught. And the integral from A to R of r cubed dr. I can cancel out the 4 pi's. Might as well. So then I can divide by r squared as well. So E would be C over r squared epsilon naught. And then this would be r to the 4th over 4, evaluated from r to A. So I would have r to the 4th over 4 minus a to the 4th over 4. This would be radially out. This one. So this is the first part. And the third part is when r is greater than b. So now we're out here. The only thing that's going to change here is our bounds of integration, because now we're enclosing the entire surface. So it's going to be E 4 pi r squared is equal to C 4 pi over epsilon naught. But now I'm going from A to B of r cubed dr. So again, the pi's cancel. So I will get that the electric field is equal to C over r squared epsilon naught. Remember we said this integral is r to the 4th over 4th. I plug in my bounds. So I get b to the 4th over 4 minus a to the 4th over 4. This would be radially out. This will be the answer. Now for question 6, we have a circuit with all these constants given. It's kept at position A for a long time. This means steady state. Find the current and the charge on the capacitor. So in this one, what we're going to do is we're going to make the current come out of the positive side of the battery. Right? But we immediately see that the only path it can take is that it has to go through the capacitor. But remember, in steady state, currents cannot go through a capacitor. So in this case, because that's the only path it can go, current is going to be equal to 0. And in steady state, remember the formula is a closed loop. Phi dot dr is equal to 0. So current is 0 because, again, it cannot flow through a capacitor. So just put this as plus Q minus Q. And if I go around the loop in this way, I would get I'll touch the positive part of the plate, right? Like if I go this way, I ignore the resistor because there's no current. I touch the positive part, what I decided to make the positive part of the plate. So I would get Q over C. And then I keep going, and I touch the negative part of the battery. So minus V. This will equal to 0. Or I just get the charge is equal to CV. I move the V to the right, multiply by C, and I get this. So again, the main thing here was current is 0 because it can't go through capacitor in steady state. So just be careful with that. Now part B is saying, now if the switch is switched to position B, starting from some famous law, which would be Faraday's law, closed loop of E dot dr is equal to negative partial respective time, B dot ds. Derive the equation that describes the charge Q on the capacitor as a function of time. So in this case, we're ignoring the top circuit pretty much. And I want to define ds going this way by convention. So ds points out of the page. And I want to make current flow in the same way as I'm going around my loop. So then I can switch up the way I label my charges now. So I can say now that I will have this as plus Q and this is minus Q. So let's start with finding the flux. The flux is going to be positive or minus Li. How do we determine that? Well, we determine that with a dot product. So in this case, because I decided to make current go counterclockwise, I need B self to either be into the page or out of the page. I need it to be in a way where I curl my fingers so it goes counterclockwise. And the way I get that is if B self points out of the page. So B self will be out. And because ds is also out, the dot product of B self dot ds will be positive 1. So in this case, it would be positive Li. And then if I need to take the partial with respect to time, this will be L di dt. And again, I like making the current go into the positive part of the plate. That's why I switched it from what it was up here, because I can say that current is positive dq dt. So now if I go around my loop, I touch the positive part of the plate, which is Q over C. And then this will be equal to negative what I found, which is L di dt. So this will give me L di dt, if I move it to the left, plus Q over C is equal to 0. But I want an equation that tells me the charge. So I got to convert current, the di dt with respect to the charge. So that would be L d squared Q over dt squared plus Q over C is equal to 0. And typically you would divide by L. So you could say d squared Q dt squared plus Q over LC equals 0. Because you would do this to get it in the form to solve it, which we'll do probably in the next step. Yeah, I want you to solve the charge as a function of time. So for this one, it's a homogeneous, but it's a second order differential equation because it's to the second derivative. For this one, you need to know that for second orders like this, your solution is going to be A cosine omega t plus B sine omega t. And for this one, you need two initial conditions. So let's start with Q at t equal to 0. So I would have A cosine of 0, which is 1, plus B sine of 0, which is 0. And this will be equal to the initial charge that I have up here, which is CV. So then A will equal to CV. Oh. A will equal to CV. And now my second initial condition is that I have current. So I need to convert this into current so I can plug in the initial condition. So current is dq dt. Right? So I had to take a derivative. Derivative of cosine is negative sine, so negative a sine omega t, and then chain rule times omega. Derivative of sine is cosine, so plus b cosine omega t, and times chain rule, which is omega. And now I put current at time equal to 0. I have a sine of 0 is 0, plus b cosine of 0 is 1, b omega. This is equal to 0 because my initial condition is that current's equal to 0. And in this step, you always solve for beta here, so just divide by omega, so you'll get beta is equal to 0. Now the last thing we need to do is we need to plug everything back into our original equation, but we have the second derivative. So I need to take the derivative one more time. Derivative of sine is cosine, but I still have a negative, so negative a cosine omega t, and chain rule omega squared. Derivative of cosine is negative sine, so minus b sine omega t, and then chain rule, which is omega squared again. So now I'm going to plug that into my equation up here. So I would have negative a cosine omega t, omega squared, minus b sine omega t, omega squared, plus q, which q was a cosine omega t plus b sine omega t over c, right? Yeah, over c is equal to 0. Well, I know b was equal to 0, so I can just drop all of this. I know what a is. A is cv. So I have negative cv cosine omega t omega squared plus cv cosine omega t over c is equal to 0. So what I can do is I can divide by cosine omega t on both sides. And I can also divide, this is LC, I was like, it looks weird. So, and I can also divide by CV. So I would get negative omega squared is equal to, if I move this to the right, I get negative 1 over LC, or omega is the square root of 1 over LC. And you should always get that omega is the square root of 1 over LC, some sort of LC. So I know you did it right. So then Q of T would be A CV cosine of omega T, which is going to be T over square root of LC, plus sine omega T, but we found that B is 0, so with the sine component will be 0. So this is our answer. So yeah, just make sure that you remember to use this one, the A cosine omega T plus B sine omega T, for second order, unlike the one we did before, which was first order, where we use alpha e to the negative beta t. Yeah, that's it. So for the last question, it's a displacement question. So find the displacement current and the current in the wire if the electric field between the parallel plates of the capacitor is this. The area of the plates is A. So recall that displacement current is epsilon naught, and then the partial respective time of the electric flux. So let's calculate the electric flux. E dot ds. E is constant because it depends on time, so E not on distance, so sine omega t. And the integral of ds is just the area, so this would be E naught sine omega t. The area we were told it was A, and you take the partial respective time of this electric flux. So that would be E naught, derivative of sine is cosine, and then chain rule, which will be omega, and then the A. So then displacement current is just this times epsilon naught. So that would be E naught epsilon naught cosine omega t WA. And this was pretty easy for the displacement current. That's the first part. Now the second part, to find the current, we're going to have to use Gauss's law and kind of derive the formula for electric field capacitance. I'm not sure if you need to derive it or you can just memorize it, but most of the tests have it that you derive it, so I would assume you need to derive it. And the way we do that is we create a cylindrical cap, pretty much. And there's only flux coming out of this cap because there's a conductor, so on this side it's equal to 0. And we define this as having an area little a. So we get E little a is equal to Q over epsilon naught. But Q is equal to the integral of sigma ds. And in this case, my area would be little a. So then Q would be sigma little a. So sigma little a over epsilon naught. I get that the a's cancel. So the electric field for a capacitor is sigma over epsilon naught. And then we use this fact and apply it to our current capacitor. So we would have E is equal to sigma over epsilon naught. And we basically work backwards. So we say sigma is now Q over A, but in respect to like our actual capacitor now, the area is big A. So this is big A. So it'll be Q over A epsilon naught. And I know what electric field is, right? The electric field was given to me as, where is this? E naught sine omega t is equal to Q over area epsilon naught. And then I just multiply by area epsilon naught on both sides, and I solve for Q. You may be wondering, why do we do this? Well, it's because I know what charge is now, and I know that current is a derivative of a charge. So if I take the derivative of this, I find current. So I would have E naught epsilon naught, the derivative sign is cosine, so it's cosine omega t times chain rule, which is omega a. And one way you can check if you did this problem right is current is equal to displacement current. So you should see that these answers are actually the exact same. If I did it right, let's see. Yeah, they're the same. So that's one way you can check if it's right. That's all the problems for this exam. Hopefully it helped. So good luck on finals.